this communication, I'm going to present tectonic and magmatic structures and processes that have taken place in the Quaternary on the lower slope of the Canary Islands. We are traveling now 300 kilometers to the west of the Canary Island. The Canary Basin here is a sector of the East Central Atlantic bounded by the Mid-Atlantic Ridge in the west, the Madeira Torres Rise in the northeast, and the Cape Verde Rise in the south. This basin includes the Canary and the Madeira Island, and a sector of the northwestern African continental margin, where the lower segment of the continental slope deepens westward to the Madeira Abyssal Plain, that dropping down to 5,400 kilometers, more or less, in this location. That dropping down, bueno, eso ya lo he dicho. In the eastern part of the Canary Basin, this one, you can see also here, take place the interference of the Western African continental margin, the volcanic province of Canary, and the oceanic lithosphere structures. The area, this area is covered with multibeam data, track lines of high resolution seismic profile, and multi-channel seismic profiles in black lines. Are the data that we use in this contribution. These are the structural trends of the Eastern Canary Basin that correspond to the oceanic fracture zones that we depicted in gravimetric anomalies and magnetic anomalies, and also in the bathymetry. The volcanic region of the Canary Island and sea mounds, more or less all this area, form a clearly differentiated relief on the adjacent seabed, and the western sector is connected, the western sector of the Canary Island is connected with this one, looking in the gravimetric, the Canary Island, and connected with these high gravimetric anomalies. Which is centered on the Echo and Bimbache sea mounts, and this area is here of gravimetric anomalies correspond with all. This one is called the Canary swell. This important volcanic relief generates a promontory effect on the continental margin of northwestern Africa, so that the lower slope of this margin extends to the west of the Canary Island, ending in the Madeira Abyssal Plain. This lower slope is characterized by the emplacement of several main landslides, proceed from the northwestern African margin and also from the volcanic island and sea mounts. Landlines or mass transport deposits in abbreviature as NTDs. Landslides are in the margin are controlled by the oceanic fracture zones marked in the region. Sorry. This one are the oceanic fracture zones, and you can see that the entities proceed from La Palma and El Hierro are controlled by this in the margin for these oceanic structures, oceanic faults. Well, this is the area where we are working. In this slide, you can see several bathymetric profiles from north to south of the study area. All the area appears with a steeped relief, more marked in several sectors, divided by the oceanic fracture zones. In the northern sector, the morphostructure related to the authentic fracture zone drove the stacking of the slide deposit proceed from the Canary Islands and turbidites proceed from the Agadir Basin. And in the central sector is the most affected by deformation that cause a set of linear scarps and elongated ridges related to normal faults. There is also characterized by the formation of several mounds in the seafloor. This set of structures produce a steeper relief characterized by terraces and scars that progressively deepen the seafloor to the west until the Madeira abyssal plain. You can see here several examples, but these structures are interpreted as subvertical faults, mostly normal faults, and subparallel anticline, syncline to monocline fault. Well, these are the two profiles, two higher resolution profiles showing the tectonic control and morphology and distribution and location of entities in the northern sector. The morphostructure control the deposition of mass transport deposits marked as NTD or high HB levels here, 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 and here, and also here. There are several landslides progressively steepened down the west. The central sector, the examples for the central sector, we have several examples for the central sector, shows a marked steepened morphology. Scarps and terrace reliefs like that. You can see this scarp or this one, or also this one here, are controlled by normal faults. And also you can see flexural deformation. Flexural deformation in this case results as several faults. We have here anticline, several anticlines in the subsurface, but also in the seafloor. These structures produce the down dip of the seafloor surface until the abyssal plain. These are examples of these faultless reliefs. Also, in occasion, this faulted relief are faulted in the axis, and in some cases also, you can see intrusion of fluidified materials. The white seismic facies correspond to probably to plastic layers, probably NTDs or fluidified units that favor deformation, while stratified facies, all this one, have a more brittle behavior. This is a complete profile, and you can see several faults with intrusions here, or extrusion include, and a wavy morphology in the seafloor that drove the progressive sink of the seafloor. Also, you can see faults of different amplitudes. Here are around 3 kilometers, 1 to 3 kilometers of amplitude, and this one have 15 kilometers. Also, you can see that in some cases, faults are related, anticlines are faulted, or you can see also the intrusions that could be from conical features on the seafloor. This is a very nice example where you can see the almost varied anticline with an NTD varied the structure, but then the NTD is also deformed. Includes you can see deformation on the seafloor. This is an evidence that the process is active in the present. We have an active folding process in this area. In this one, you can see also that the intensive faulting associated with some case in some areas with the anticlinal ridge, and here there is an intrusion, but don't arise to the seafloor. It produces an intrusion lateral that is known as a seal. This is the diatrema and the seal, horizontal seal intrusion. And also vertical intrusion a favor to the intense faulting. Well, this is the southern sector, and this is more less deformed sector, where there are several entities proceed from the Saharan sea mounds, from Eco sea mound, from the Pap sea mound, and these entities are successively faulted and filling depressions in the margin. But faults control the thickness of the entities, and the entities look here that have intrusions also to the surface. This is the last example. This is a profile, high resolution profile crossing the fracture zone. And you can see first the sedimentary units controlled by the faults, and an intense faulting reacted with the ridge. This is you can see these structures in multi-channel profiles. The surface is not so interesting now, but you can see several intrusions here. And this intrusion proceeds from the subsurface, almost the basement. And in this case, you can see a basement height here, and a conical structure, a volcano, over the basement height. This is the map of faulted scarps, anticlinal ridge on the seafloor, and mound distribution. The three types of the structures have a coincident north-northeast, south-southwest trend, and this trend corresponds to the oceanic fabric generated during the spreading oceanic phase. Analyzing bathymetry and seismic profiles, it's possible to differentiate two basic types of mounds in the area, domes and cones. This is a special case, it's an outlier that appears in the area. We call it Garoe Mound or Garoe Bulge. It's a kilometric structure with a dome type, but it is faulted in the axis and in the flanks for several normal fault depressions. This is domes. They are rounded and smoothed, positive release interpreted as a positive pressure deformation generated by fluids injected over seal intrusions into the sedimentary cover. This could be the seal intrusions that generates the injection of fluids to the upper section of the sedimentary cover. In part, the fluids are generated by the heating of poured water and organic material present into the sediments. The deformation will be caused in surface by the rise of these heated fluids. The second type of mounds are volcanoes located on the seafloor, produced when silt intrusion cross all the sedimentary cover. In this case, intrusions form volcanic edifices here. Over a basement height along a probable branched hydrothermal volcanic system. But there are several volcanic cones proceed from silt intrusions and places at different depths. They could proceed from basement height, but also could cross all the sedimentary cover, as the example of the Tenores volcano. This one has 3 cones that we named the Tenores, 1, 2, and 3. This is the expression in multi-channel seismic, and this is the expression in high-resolution profiles. In multi-channel, you can see chaotic phases in surface. This corresponds with the accumulation of material in form of a become, one cone in the subsurface and one cone in the seafloor. Over a diatrema, where it corresponds to the chimney, the conduct of flow of the material. In the high resolution here, also you can see that material extruded in the border of the structure. We call it the outer rings of the structure. We study especially these 3 volcanic cones, and we obtained 6 gravity core on this area, 4 of them in the cone 1. This allows us to know what is the sedimentary or material that form these structures. Well, these are mounds constituted by an accumulation of hemipelagic sedimentary units, the brown material, and layers of volcanic tephra, as this one, and also this, and here are marked with the double red arrow. This volcanic tephra appears also with basanitic rocks over blue and green hydrothermal clays, this one, that correspond to smectites rich in aluminium. These volcanic rocks are basanites or OIV type, and the potassium-argon dating of the rocks have given values between 800,000 and 1,600,000 million years. They correspond to Quaternary activity. And the edge of the tephra layers have been estimated from the sedimentary rate. We use a 1 centimeter per kilo year. That is a measure obtained from ODP wells in the area, obtaining values from 88 to 257 kilo years, also Quaternary age. Well, the conclusions. The volcanic region of the Canary Islands has a very long activity. The seamounts of the southwest of the region are results of the Mesozoic activity. From this later, the activity moved to the north of the region, and since that moment becoming more modern towards the west of west. As a whole, this activity has led to the formation of the Canary Seal, a stronger market in the gravimetry. Toward the west, a flexural effect should produce a reactivation of the west-northwest oceanic zone of fractures and normal north-northeast south-west trending basement faults, which progressively produce the sinking of the margin towards the abyssal plain of Madeira. Normal basement faults reactivation have produced the deformation of the sedimentary cover, forming the different faults observed, as well as the wavy or steep relief of the seafloor. And a second effect of this reactivation is probably the generation of a differential topography at the lithosphere base, which drove the adiabatic elevation of mantellic magma, producing intrusion in the form of interstratified silts in the sedimentary cover or inclinated silts in favor of the basement faults. Intrusions given rise during the Quaternary to the formation of hydrothermal and magmatic complexes, which have generated a series of volcanic domes and cones on the seafloor. And thanks.
And we try to speak about the different submarine phenomena or processes and also the deposits. Well, the lecture is divided in several themes. At the beginning, we speak about the two textural category in the volcanic rocks, coherent volcanic and volcanoclastic. After we speak about of lava and thin volcanic intrusion by the pyroclastic deposit, by red sedimentary eruptive volcanoclastic deposit, volcanogenic sedimentary deposit, and finally, we try to explain the architecture of the lava delta from the last eruption in La Palma. Well, coherent volcanic texture formed by cooling and solidification of molten lava or magma. For example, this Peru lava. Volcanoclastic is described to deposits composed predominantly by volcanic particles. You can see the Peru lava fragment breccia. Volcanoclastic deposits are classified in the basis of class-forming processes and transport and depositional processes in autoclastic, pyroclastic, resedimented syneruptive volcanoclastic, and volcanogenic sedimentary. Some example is shown after. Autoclastic volcanic primary volcanoclastic deposit made of particles, it is named autoclast, generated by in situ non-explosive fragmentation of lava or magma, autobrecciation and quench fragmentation, and are named autobreccia, ioloclastit, and pepperit. Autobreccia is a glassiclastic deposit formed by non-explosive granulation spalling of solid lava ring as the result of the deformation. The fragmentation is generated by dynamic stretching of molten lava. This can you see another type of autobreccia, is the submarine dacitic autobreccia from Cabo de Gata in Spain. Ioloclastit is a glassiclastic deposit formed by non-explosive thermal granulation spalling of solidified lava rings. The fragmentation result for the quench fragmentation of molten lava. This is a micrograph of blocky hydromelan glass fragment from Simon 6 deposits from about 2 kilometers deep of exit of the East Pacific Ridge. This is another ioloclastit. In this case, is in situ rhyolite ioloclastit. Is from Ponza, Italy. Pepperit formed by parts of intrusion that are fragmented by quenching and contact with wet and consolidated host sediment. Pyroclastic deposits made of particle pyroclast generated by explosive eruption and redeposited by primary volcanic processes, flow or surge. Resedimented sun-eruptive volcanoclastics from rapid sedimentation of textural unmodified freshly eruptive pyroclast or autoclastic particles. You can see, for example, resedimentic dacite hyaloclastic from Milos in Greece. This is another sample for the resedimentary basaltic hyaloclastic from pillow lava fragment Brecha, is from lava delta of San Andres here in Tenerife. And another example for Canary, the resedimentary pillow lava fragment Brecha in the Barranco Las Angustias in La Palma. Volcanogenic sedimentary are composed by aggregates contain particles derived by erosion of pre-existing volcanic deposits and they were subject to significant reworking prior to final deposition, or that were deposited long after eruption. This is an example. This is Volcanoclastic sandstone from the Barranco Las Angustias. It's submarine volcanoclastic sandstone. Another sample for La Gomera is submarine volcanoclastic sandstone and siltstone from the Barranco La Higuerita in La Gomera. Taking into account the viscosity is the property that most influences the style erosion, we distinguish between basic and acid magma to speak about the coherent phase, lava and volcanic intrusion. Basic lava flow are produced in effusive eruption. Submarine basaltic lava differ morphologically from subaerial lava due principally to efficient crash formation, quenching, that result for eruption into cold seawater rather than air. The quenching rate in submarine basaltic glass is often several orders to magnitude greater than in air, a consequence primarily of the high thermal capacity of seawater. The three primary types of submarine lava based in morphology are pillow, lobate, and sit and lie along a spectrum distinguished from one for another by the size and interconnections of the unit cell that make up the lava. Pillow lava are composed by meter scale, poorly connected valves of lava. Lobate lava have large, 5 to 10 meter wide, moderately connected path of lava, and sit lava completes fully connected sheet of lava. This is the photography for different type of this lava flow. Pillow, lobate, and sit is for the above of the sea surface. Submarine lava that advances slowly relative to rate of the crash formation produce pillow lava, while lava that advances quickly relative to crash formation rate produce sit lava. The lobate lava is an intermediate type. Felsic lava and dome are producing in effusive eruption also. Regardless of letting felsic lava and high viscosity and produce lava that are thicker and less extensive than basaltic lava. Submarine felsic effusive eruption generate tabular lava, equal dome-on-dome complex, and low hyaloclastic lava. Felsic tabular lava and dome erupted underwater are similar in size and shape of the subaerial counterpart. They are typically thick, tens to hundreds of meters, but short for tabular lava, hundreds of meters, around 10 kilometers. Felsic lava, tabular lava are mainly composed for coherent phases and can be crystalline or partly crystalline and partly glassy. In situ hyaloclastic occur at the base, top, and margin. Crash rotate hyaloclastic and resedimentary hyaloclastic may be present at the margin adjacent in situ hyaloclastic. Submarine felsic dome and dome complexes are typically thick, tens of 100 meters, but short for dome tens to a couple of 100 meters. In submarine felsic dome, in situ hyaloclastic surround the current core through the proportion of hyaloclastic versus coherent phase vary widely. In situ hyaloclastic may grade outward to class rotated and resedimented hyaloclastic. Some felsic submarine domes are entirely glassy, and some have zones of pumice hyaloclastic and pumice coherent phase. Low hyaloclastic lava consists in multiple coherent domains of loop, meters to 10 of meters across, separated by domain of hyaloclastic. The lobe form where viscous molten lava emerges from a feeder dike that intrude cogenetic hyaloclastic. The lobe detached from the feeder dike are pushed aside as more low and more hyaloclastic form at the dike. These processes can create a lava units tens of hundreds of meters thick and on overlaid tabular or dome morphology. Finally, cristodomes are high-level intrusions that cause updoming of the overlying sediment of rocks. Cretodome and other Felsic intrusion in some cases include a marginal domain of glassy monomictic breccia that show fit texture. This breccia passes outward into monomictic breccia in which clasts are separated by narrow stem of the host sediment. This texture implies the magma is contact with a wet sediment was fragmented by quenches during intrusion, forming blocky pepperite. For a pyroclastic deposit, a submarine pyroclastic deposit, the hydrostatic pressure is a formidable impediment to parallel magmatic explosive submarine eruption of basalt, which typically have low pre-eruption volatile content. Nevertheless, for the right combination of depth, volatile evolution, and coupling, and magma-water interaction dynamic, submarine explosive eruption of basalt are possible to depth of the few kilometers. Only two small submarine explosive eruptions have been observed at their bend, providing information about submarine explosive eruption dynamic that can only be gained by direct observation. Is Northwest Rota 1 volcano in Mariana Arc and the West Mata volcano in Lau Basin. Northwest Rota 1 volcano is in Mariana Arc and is 560 meters below the sea level. You can see the photograph of this activity in the Northwest Rota 1 volcano. Now we can see a video of this activity. You can see certainly an explosive activity that produce a pyroclast. Thank you. The next, please. And for West Mata volcano in Lau Basin, in this case is 1,200 meters below sea level. You can see the photograph, please. And the activity, you can see the explosion and they produce a pyroclast like the previous volcano. Thank you, please. The next. Well, another type of macro eruption observed in the surface is the formation of the lava balloon. Mafic submarine eruption can form large floating balloon class along with seawater discoloring fine. Balloon diameter runs from several tens of centimeters to a few meters and are buoyant because they have large interior cavity or core or frothy silicic glaze, is xenopumice or restingolitas. Strong decompression during ascent allow rapid expansion of gas inside the balloon so that bubble collapse and the balloon inflate. Another type of mafic eruption observed in the surface is the Sarseyan volcanism. Sarseyan eruption is an explosive style of volcanic eruption, hydromagmatic, that take place in shallow sea or lakes when rapidly rising off and fragmenting hot magma interact explosively with water and with water steam tephra slurry. The eruption style is named after the eruption of the south in the south coast of Iceland in 1963 that caused the emergence of a new volcano island, Sarsay. Fragment into small pyroclastic, ash and lapilli, and this accumulated around the crater to form a small cone or ring-shaped hair. Sarseyan eruptions are characteristic and steady, with phases with rapid repeated short, violent explosions separated by marked quasing phases dominated by steam generation and condensation. Another type of mafic eruption observed in the surface is the lava delta. When the lava enters in the ocean, it forms a broad volcanoclastic delta traversed by lava tabs. Interaction with seawater becomes most explosive when the lava flows in high amphicruces in relatively few tabs. Major littoral explosions are often linked to external mechanical triggers, such as cracking of collapse of the lava tube or vents collapse. Activity in this case takes three dominant forms: episodic tephra jet, liquid-rich direct explosion, and bubble burst. The tephra jet, this activity is linked to severing of lava tube by vent collapse. Breaking waves that disturb the steam of the melt, producing closely spaced section of tephra jet up to 10 meters high. This activity results in two types of eruption produced: proximal littoral cones, with gain grown rapidly at a rate of several meters per day, and a downwind tephra blanket. Directed explosion occur during collapse on unstable lava delta. Incandescent vent phase are exposed and both into contact with seawater with trigger explosion ejecting block from the hot wall rock of the lava delta and lesser amount of fluid lava. Ballistic clash and produces and disperses significantly more widely than tephra jet, and the ejecta from discontinuous and asymmetrical block file that can extend up 200 meters inland. On April 19, in 1993, a collapse killed one visitor at the result block EF4 injured several others in Hawaii. Bubble burst is a process that traps water, for example, fracturing of the roof of the lava tube, close of the sea level, might produce 1 to 10 meter diameter steam bubble. Explosive rupture of the bubble eject a mixture of fluidal pyroclast, limu upele or pele hair. On rare occasion, that fracture instead produce continual fountain lasting tens of minutes. And it's possible also pyroclastic deposit with silic eruption is related to caldera and composite volcano. Submarine eruption of most evolved magma have formed lava domes, pyroclastic cone, and caldera. Modern submarine caldera are circular or elliptical and between 2 and 10 kilometers across with a flat, slight concave floor, 1 to 7 kilometers wide, underlaid by pyroclastic deposits. Their walls raise a shallow slope, 14 to 30 degrees, up to 1 kilometer above the caldera floor. Submarine caldera are of similar size, submarine caldera, and SAPI for similar large and explosive eruption process. Here you can see the deposit for this eruption, and consistently mainly inferior density current deposit made on pumice and ash with a very small proportion of lithic fragment. Units are 1 to 10 meters thick, diffusely stratified and poorly sorted with upward quartzing of pumice. Parallel to wave diffuse stratification is defined by alignment of pumice class, especially at the lower half of each unit. Now we speak about the architecture of the lava delta from the last eruption in La Palma. On September 28th of 2021, 5 minutes, thank you, the lava reached the coast in the subruin of La Playa de los Guirres on the whole lava delta formed in the last eruption in 1949 of San Juan volcano, beginning to form a lava delta. At different times of the eruption, the lava reached the coastline, giving rise to the formation of 2 different lava delta. Lava delta, similar to river delta, for whether sufficient subaerial flow of the lava enter standing body of the water. The lava cools and breaks up of the encounters the water, with the resulting fragment filling the adjacent topography such that the flow can move further offshore subarea. In the Canary Islands, this formation are called Islas Bajas, no Fajana. Lava delta structure. Well, in the lava delta, you can see 2 units. The top unit is a horizontal lava flow with columnar jointing, and forested unit with pillow lava and geological breccia. You can see here the representation of the structure of the lava delta, note how the passage zone mark the contemporaneous water level. The southmost delta de lava in this La Palma eruption begin the most voluminous and actually representing the amalgamation of 3 temporary delta initially separated for one for other for process expanded to make the main delta. The total area of the new lava delta is around 48 hectares. You can see, please, video. You can see the first lava delta. The next, please. And you can see the lava go down above the cliff, and the formation of the lava delta that move over the old beach. And here, on several occasions, when the lava came into contact with the seawater, a small hydromagmatic explosion occurred and small tephra jets were produced. You can see now this Tefrajet. Please, the next. The lava flow over the Salu Kose platform around 60 meters deep, giving rise to the typical AA flow you can see in the photograph. Please, the next. And more deep appear the mega pillow lava. You can see the video for the Spanish Oceanographic Institute. Okay, the next. On the edge of the pillow, you can see the ground marks, symmetric traverse springy cracks. It's very easy to see here. And more deep, breccias of fragment of haloclastic and redistributed pillow lava fragment breccia appear, produced by gravitational collapse, mostly a grain flow, of the lava flow that are found at less deep. You can see the different ground flow deposits. It's typical, this very good selection of the class. And in some of them it's possible to see this inverse gradation. The biggest fragments are in the top, in the lower part, the fine. This is typical for the grain flow. Well, thank you very much for your attention.
Thank you, Eugenio. Thank you to the IEO, the Felsic, for this invitation to share all the civil protections ideas in this area, in the volcanic risk management in the Canary Islands. And I hope you can understand me. Sorry for my English. I will try to do it as my best. So in Spain we have the civil protection is regulated by a Spanish civil protection law, with these actions that you can see there in this picture, and in these actions, the public administrations, we have to do a lot of actions involved of every one of them, like the anticipation, the prevention, the planning, the information to the population before, during, and after the emergency, the management in the moment of the accident or the emergency, and very important also the rehabilitation, and very important also in this case of emergency, in the volcanic emergencies that we know that nowadays we're still working in the risks. Also we have basic guidelines for civil protection planning in case of volcanic risk. Is also a guidelines of the Spanish government. In base of these basic guidelines that exist also for another risks. In the Canary Islands we have a plan that is called PEVOLCA, and is the plan that we have to we have to consider to manage all the situations in this case, before, during, and after. So there is a picture of the PEVOLCA's organization. It's very similar in other emergency plans that we have in the Canary Islands, but with a special difference that is not in another plan, in another civil protection plan that I've never seen before, and I have for 20 years of experience in this area. But this risk in the Canary Islands is there is a specific committee with the scientists of the Canary Islands and the Spanish government that are monitoring and inform to the direction of this PEVOLCA to take the decisions. You can see the management and coordination structures there. Also, there are the action groups below for intervention, security, the medical assistance, logistics, or technical area. And as I was saying, there are a group of scientific organizations called PEVOLCA Scientific Committee, that was activated by the civil protection authorities in the pre-eruptive situation, during the eruption, and still now in the post-eruptive situation. We can see on our left there are like two groups, well, it's not very difficult, two groups involved with the scientific committee, but in fact we had only one in this emergency, and also with another structures like the committee assessor, like is a committee for the direction of the plan. But you have to know that all the days that we have this emergency was very complicated to have all the structures activate every day. So we unificate some of these structures. So in this case, the scientific committee was only one structure for the scientific information and investigation. So during the eruption, our actions for the civil protection was the activate of this plan. This plan was activated in different phases. In the week before, in a phase called alerta, like an alert, is the same phase that is activated nowadays, but during the eruption was activated in the high level, that is the emergency situation. This emergency was managed always by the Canary Islands. This is very important to say, because this is always the possibility to direct the emergency from the Spanish government if necessary for any reasons, but we have to say that in Canary Islands we could manage this emergency with our plan, also with resources of the Spanish government, like in other situations in forecast and the fires now this summer. But the direction, the structure, the organization was in the local government in the Canary Islands. Also, another action that you know for sure is the volcanic red traffic light that we informed to the population in the moment of the eruption. Also with the yellow traffic light the week before, and nowadays this yellow traffic light is activated in La Palma. The daily meetings of the scientific committee and the steering committee, the direction, daily operative and communication strategies from the advanced command post, the dimension of the resources, the organization of the civil protection volunteers, that was very, very important and necessary in this emergency, in too many works. The daily communication to the population, this is very, very important to remind the communication to the population every day, in the morning and also in the afternoon, and whatever, if there is any change or any situation that we have to explain to the population, is important to be ready at every moment. Not only the public administrations, also the scientific committee was informing directly to the population. We think that is a very important thing also, to listen the technicals, and population prefer always to listen technicals than politicians, and I think this is very important. We have to improve this. We have always, every day was like more than 18 days of eruption. It was like every day was a different emergency, very different for the meteorological situations or whatever. We have more or less resources, any problems, gases, ashes. So every day was a different emergency. I think we thought as emergencies as days we was the eruption on. So it was a very stress situation to guarantee the access, also the population in the restricted areas in a security, in a sure situation. It was a characteristic of this emergency. I think the public administrations was very ¿cómo se dice? Valientes, very brave to, thank you, very brave to try to facility to the population was the going on day by day instead of the emergency also. So every day we have to redefinition the risk and self-protection message for the population, because every day was different, these self-protection messages. Another actions, you know, the evacuations, the confinements also, the access restrictions of the affected area via QR code APP. The roof and the street cleanings to avoid the ash accumulation was people was very afraid about this situation about the houses. They were very, very preoccupied. The project actions for telecommunications, electricity infrastructures, the restricted airspace drones controlling by drone flights, not possible in another way. That the only information we have was with the drones. There is not any possible to go like a visual road with like we can do in the fires, for example, no, but in this situation was impossible. So only with drones was the only way to have information, images or videos. Also, the 2 portable desalination portable plants for water, and the reconstruction of the road system in the west of La Palma during the emergency. It was a very stressed also situation, because these actions normally are before the eruption. When the eruption stopped, we have this kind of actions of recuperation, but in this situation was very necessary, and well, we was working in this during the eruption. The real-time monitoring the air quality stations, very important to protect to the population for the gases, principally. The aerial and marine exclusion zones, and guarantee the communications for all the participants. We was working also during the emergency in a new specific education protocols, new protocols in a different ways. There are some examples in the education area, or the specific public health protocols also for people, evacuation, confinements with the maps of with the lava flows and the zones that was the restricted areas, or the indications that was directly communicated to the population. And we defined in the beginning an restricted area, a size of 2 kilometers in the beginning, and as the eruption was going on, we was modifying and adapting this area near to the lava flows and the areas that the scientific committee explained that was the security zones, that people cannot be near these lava flows, and the risks that could be like a consequence of this access. The specific access protocol with this QR access to make easy to the security agents to know who is allowed to access or not, but it was a very difficult work, because we have to comprove see if you really live in the zone, or you have a work situation that you can enter to this area. So it was also a very stress situation. And this is with a minimum requirements of the self-protection also for the population. The restricted zone for drones and for another drones or couldn't access to this area. The gas monitoring with these two yellow alert and red alert to know how the gases was going on in the zone. If there was, for example, security or intervention agents in a risk area, to communicate that in this area they have to exit or go to another security zone. And this is for finalizing. I will talk about the advanced command post. I want to explain to you that we was in two different situations of the PMA or advanced command post. Normally, we are in a same situation in emergencies that so like during like 1 week or 2 weeks, but not 3 months. So we was for 1 month and 10 days in a open area in La Palma with all the different emergency services that you can see this in this logo. And there's a lot of actions in this advanced command post, like the coordination meetings, the reception of authorities, the visualization of drone flights directly, the establishment of the communications, also the different protocols that we talk now, the scientific staff accreditations. This is another characteristic of this emergency. The scientific committee steerings, committee meetings, gas detection equipments, and also training about manage these equipments that was new for too many people that was working in this emergency. And the second location, we was in another space, not in the outside, just in the inside, better for the weather, ash, gases, but I think we lost functionality due to the type of building and facilities like rooms. It's very strange for me to be in an emergency building or rooms. Well, I think we continue with our functions. There is an example of different tools, intern tools for us for the management of the emergency, but also maps or tools for the population. I think we have to improve too much in this, because we have to show maps more comfortable for the population, more easily to know which is the area, restricted area, what can I do, what I can do. So I think we have to improve and make it easy to the population. All this information, this was always the maps, these kind of maps always are very important. At the first moment we began to work in a map, physical map, later on, obviously we was working with the technology and GIS. This is important because we began to use the same language for the different firefighters that was working in this emergency, because there was people of different islands and also for Spanish. So they began to use the same language, and was the first time, and it's very, very important to say. The Cabildo also developed a visor of mapas for population, the evolution of lava flows and photos. So, and we realized about the importance of the technology in this emergency. We was always working in daily action plans with the affections, daily affections, and the evolution of the day we thought we will find this day, and all the services that we was working, and also the people that can enter this day to their houses or to work, because it was divided for days and zones. So to finish, I will share these slides with the learning and experience from the La Palma volcano emergency management. We need for an update special volcanic risk plan in the Canary Islands. We have to improve too many areas, and so add new groups, for example, like the air quality monitoring and all the gases is in an area that we have to add in this structure. The strengthening of the civil protection system at all levels, municipalities, town councils, regional government, state government. The integration of the role, but improve also this integration of the role of the science in the civil protection to difference what the scientific needs for themselves. They have to discuss, they have to argue, and perhaps what the civil protection needs is another thing, that we have to know exactly what we need from the scientifics. And this is, I think, it will be can be better for all of us. 2 minutes, yes, I'm finishing. The importance of these long periods of volcanic inactivity is very complicated to be self-protected the population. So the perception of the risk is very important in these situations that are not frequently, and well, we have to work in this with this situation. And also the exercises and formation of the administrations and emergency services is a task that is to do. After the eruption, the PEVOLCA is activate. The scientific committee remains with the. I think every 15 days they are monitoring all the situation that remains in the west of La Palma for these gases. So there is a lot of instrumentation in this zone from the government, but also now with the scientific administrations, and the Cabildo de La Palma also are implementing new instrumentation to be informed of these levels in this area. So we still monitoring with fixed gas measuring equipment, sensors, and other equipments. And thank you very much.
I'm super happy to be here. But before starting my talk, let me bring some ideas that you already mentioned this morning. You were saying that we still have a temperature anomaly of 2.5 degrees Celsius in the water column. So let's see what's going on when we measure the temperature directly from the hydrothermal fluids. Yeah, and also I would like to tell Pablo, yeah, that this morning you mentioned that you were very interested in the nutrient fluxes, so you are very happy. You would be very happy because I have some great news for you. Yeah, so my talk is about the characterization of the hydrothermal fluxes. Yeah, so I'm gonna characterize not only the amount of water that is coming out from the volcano, but also I'm gonna define the actual active area, and I'm gonna tell you about the heat and the nutrient outflows that is happening there. For that, we have developed very fancy instruments. They were completely designed for our team. So, yeah. Yeah, and it was a very multidisciplinary survey. So yeah, let's start. For the spatial distribution of the total active extension, we use the ROV, the Litopus 2000, and we explored the whole edifice from all the secondary cones up to the main crater over here at 127 meters depth, up to the summit over here at 88, 89 meters depth. So In total, we explored for this study during 5 different years in a total of 46 dives. So we collected like 100 of hours of video that, of course, I already analyzed. Yeah, so we also measured the temperature from the fluid, as I already mentioned, in 3 different years and in a total of 58 stations. Here you can see the whole distribution. Here is the main crater up to the summit. And you see all the different stations sampled in different years. And to do that, we use this temperature probe that was introduced into the sediment, like 20 centimeters depth, just to see how was the temperature of the hydrothermal fluid before it goes up to the surface, just to avoid the dissipation of the heat. Then we also measured the velocity of the fluid. To do that, we designed this instrument that was deployed by our ROV. So yes, once we see an interested area, we put it on the floor, and yeah, and so the fluid go up through this base, this chamber, go up to this transparent ungraduated pipe, and we observe all the particles going up along this tube, and that's what we use to measure the velocity of the hydrothermal fluid. And in total, we deployed 30 different stations in this study area. And also, to sample the fluid, the hydrothermal fluid directly from the vents, we also developed this kind of syringe that is a piston-driven suction device that was also deployed by the ROV in 9 different stations in a total of 2 years. So as you can see, in a range of from the 2014 to the present, we have developed all these studies, so we have a robust database. So analyzing all this image from the ROV, we delimited the active area, and there is this red dash line over here. This is the area. And you also can see the ROV tracks. And we obtained a total area of 7,600 square meters. And I don't know if you are able to understand this number, but it's kind of similar to a professional football field. Or I already checked yesterday, is also the same area as this building, so you can have an idea of how big or is the active area here. Here is the crater, and then you see all these dots. All these dots are different kind of venting structures that can be a diffuse area, chimney-like vents, small orifices, small bacterial mats between rocks and cracks. So it's very complex, this area. But we were able to account for like more than 3,000 individual structures. And then also, of course, very large and flat diffuse areas. From these dots, we could estimate the density of individual vents, and you see that they are not even distributed along the all active area. They occupy mainly the central area, like this is like a crest going up to the summit. And we also observed that the vent densities varied from 0 to up to 27 vents per square meter. And also we can see that the density between 0 and 1 is the dominant regime here. So here we have the temperature results and the velocity results. Each dot is the station location. And again, we can see how different the temperatures are, that they vary from 21 up to 33.3. So we have a variability of 40.4 Celsius degree, and these differences are even very, very close. As you can see here, there is a cluster of stations, very hot, and here in a couple of meters away, we have a kind of colder station, and also here. And again, this kind of pattern we can see here, that we have a high velocity here and a low velocity station here. And also we see how variable is the velocity. So we wanted to know what can control or what can decide this uneven distribution of temperatures and velocities. And that's why we try to classify all the stations depending on the venting structure or the geomorphological structure. That's why we classify all the stations into a group of diffuse stations, transitionals, or focus. The diffuse station, you see that they are very plain, even. They have these bacterial, microbial mats. The presence of rock is very limited. Then the focus stations are mainly located in rocky areas with a high density of orifices, and the transition is just a kind of mixture of these regions. So doing that, we have the same figures as the previous one with the location of all the stations, but now they are colored by the venting structure, the different venting regime. And the temperature values here were interpolated just to cover the space between stations, the same as velocities. And again, we see that the higher temperatures are located in the rim of the crater, but it's not the same behavior as the velocity, that we have the highest velocity here, close to the summit, and outside in the west side of the crater. So again, we don't know, that's the visual interpretation, but we don't know what's going on there. So if we see the values, the numbers, and we classify all these stations, here we see how if the group of stations classified as diffuse for temperatures and velocities, that we find, that the temperature is going to increase from diffuse to focus, and also the velocity is going to increase from diffuse to focus stations. And it makes sense because in a flat and diffuse area, the venting fluid is going to escape easily, and the temperature is going to dissipate easily as well. And on the contrary, in the focus area, the hydrothermal fluid has to escape through narrow conducts, and the temperature is going to be dissipate more difficulty. So we wanted to also see if the vent density has any kind of relationship with the temperature. And we don't see any clear pattern, but what we can see is that at high density of vents, only high temperatures are registered. Meanwhile, the lowest temperature are only registered at low vent densities. Okay, so with the temperature and the velocity of the fluid, we could estimate the heat fluxes. And this is the equation where we have the volumetric heat capacity that we just use this number from the reference. And here we have the velocity and the anomaly of the temperature and the area. And that is the parcels of or the beams of this interpolated map. So as result, we have this spatial distribution of the heat that it can vary from 6 to almost 150 kilowatts per square meter, and with a mean of 30 kilowatts per square meter. And if we extrapolate this value to the whole active area, that is the red dashed line, we obtain almost 230 megawatts. Probably you don't know how much is that, but if I tell you that it's 10 times the capacity of this 100% green energy production project that is installed in El Hierro, so it has this volcano has 10 times the capacity of this project, and this project can cover the whole demand of the island. So you can see how much it can produce. Okay, yes, to finish, here we have the results for the nutrients. I'm not gonna get in detail, but here we have the concentrations that ALBA already estimated in a previous study. And we can say that they keep steady, so the Tagoro is producing a huge amount of nutrients. And here we can see the enrichment for the silicates. We can say that Tagoro is emitting 100 times the concentration that we can find in the ambient seawater, and the same for the phosphate, 25 times, nitrates and ammonium. And here we have the flux per square meter, this huge number here, and this is the estimate flux for the whole active area. That is massive. And even for the nitrates, we can say that it's comparable to the Mauritanian upwelling. Yes, that's all. Just to conclude, say that Tagoro submarine volcano represents one of the few intraplate submarine volcanoes thoroughly described worldwide. Here we describe the spatial distribution, and also we saw that the fluid temperatures and velocity exhibit a patchy distribution, and higher values observed at focus areas, and also that the heat and nutrient fluxes contribute significantly to the release into the shallow region of the ocean. Thanks.
Okay, so good afternoon. Thank you, Eugenio, for the introduction. I think that this is the bad one. Okay. No? Yeah. And also thank you to the organization committee for the opportunity of showing this work that we conducted through the Volcana project from the Spanish Institute of Oceanography. And last year I presented some preliminary results of this work, but today I'm going to show the whole story about how the current hydrothermal vent fluids from Tagoro are influencing the marine microbial communities nearby. So I will be really brief with the introduction because we've been talking about Tagoro and El Hierro all morning. So the eruption of Tagoro occurred in October 2011. This eruption produced an abrupt changes in the physicochemical properties of the water column that altered the local marine microbial communities. In this case, small phytoplankton abundances decreased, whereas heterotrophic prokaryotes were more abundant and active during the eruptive phase. Since April 2012, Tagoro entered an active degassing phase involving the release of heat, metals, nutrients, and gases from multiple vents, as Juan Pablo already explained. However, the extent of how these hydrothermal fluids were influencing the marine microbial communities that live there is unknown. So this is where our experiments came. We developed an experimental approach. We conducted 4 experiments during 2 oceanographic cruises, one in April and the other in October 2021. For that purpose, we collected samples from 2 vertical hydrographic stations, one located in the main crater of Tagoro and the other one in unaffected waters that hereafter we will call reference. So each experiment consisted in 2 replicate control bottles and 4 bottles that were enriched with different proportions or volumes of filtered Tagoro's hydrothermal fluids. This treatment strategy allows us to have an initial microbial community that was never affected by Tagoro before. So the additions resulted in an increase in silicate concentrations in our bottles, and as we can see, followed the proportions of hydrothermal fluids that we were adding. No? However, as we can see, the dissolved concentrations of nitrate and nitrite and phosphates were quite similar between the volcano-treated bottles and the control bottles. So why we chose these additions? It was based on previous studies on Tagoro, in this case, a study of Alba. As she found out that dissolved silicate concentrations in Tagoro were a mixing tracer of hydrothermal activity in the area. So that's why we chose silicate concentrations anomalies below 2 micromole per kilo, because we wanted to study not only the response of those organisms closer to the main sources of Tagoro's hydrothermal fluids, but also those areas where a strong dilution of macro and micronutrients occurs. So, well, I will jump to the results because I think that they are quite interesting. Here we have the phytoplankton biomass using the chlorophyll A concentrations as a proxy. We monitored daily this response, and as we can see, our volcano-treated incubations, the ones that we added different proportions of hydrothermal fluids, were showing more biomass and were increasing faster than the replicate control bottles, which is the gray color. I'm using this first one, but these are the 4 incubations. And we are seeing the same kind of response in the 2 seasons. And if we check, for example, only this exponential growth phase, the gray shaded area is the one for the control bottles and the yellow one for the volcano-treated bottles, we can estimate the apparent phytoplankton growth rates. And here, this evidence how our volcano-treated incubations were always having an increasing growth of phytoplankton in comparison with the control bottles. So until now, we knew that phytoplankton was growing, was with higher biomasses in these volcano-treated incubations, but we didn't know who was the responsible of this increase and which were the organisms that were like benefiting most of these hydrothermal fluids. So we started checking the flow cytometric results and pointed out to the Synechococcus species of cyanobacteria. So we can see it has this quite the same shape, or we will say a similar shape than the graph before. But the picocaryotes were the ones that really were increasing this phytoplankton biomass. And we can see, for example, that the abundances of cells were higher in comparison with the Synechococcus. However, both are major contributors of this small phytoplankton size fraction, which is called picophytoplankton, and comprise organisms that are around 2 micrometers. So this response is adequate and is in line with the previously observed on other phytoplankton blooms. But however, we conducted molecular analysis, and here is where everything came to be more interesting, or I think so. And we saw that we got 3 main organisms that were responding to these hydrothermal fluids. This was dinoflagellates, ochrophytes, and small green algae. All of them are small photosynthetic eukaryotes, so they have a size of 5 micrometers maximum. So, okay, so don't panic with this graph. Here we are looking forward to the taxonomic rank levels. So now I said that we saw some dinoflagellates, ochrophytes, and small green algae, and now we will see in which class they are. In which class they are identified. So first, the dendrogram representation gives us a hint on how the eukaryotic communities differ between samples. So here we are seeing in every incubation that the control bottles were always similar and very different from the volcano-treated incubation. So this is saying that something is happening in these hydrothermal treated bottles that is not happening in the control one. So that is very good. And also, starting with the small green algae, we are seeing that the Chloropicophyceae is the most benefited or most abundant ones. Then, if we see the Stramenopiles, we see the common Bacillariophyta, which is the diatoms, and Pelagophyceae, which are also diatoms. Well, we call them heterocons because they have different functions, but we all know it's small diatoms. And also something interesting is the dinoflagellates. Okay, now we are seeing that we have 2 types of dinoflagellates: the Syndyniales and the Dinophyceae. Syndyniales is a group of parasitic dinoflagellates. In fact, as we take a look to the family class, in the family level, we are seeing 3 types of dinoflagellates that are identified for parasitite other dinoflagellates, like the Gymnodiciae, which is the 4th most abundant dinoflagellate in our incubations. Also, some diatoms like the polar-centric Mediophyceae, which is the most abundant one in our incubation. So. We have the theory that these dinoflagellates are a result of our bottle effects, of our incubations, like they are living of other organisms. So we have to check the other organisms to really see the link between these hydrothermal fluids additions and the microbial response. And that's where the thing is really interesting, because we see that diatoms, the polar-centric Mediophyceae and also the Raphid pinnate were the most abundant in our volcano-treated incubations, and also the Chloropicophyceae small green algae. And also, we wanted to go further, and we have done an analysis to try to have the species that were characterizing our volcano-treated incubations. And as we can see, we have the Chloropicon roscofensis, which is one species involved in the latest family that I've been talking about, and has great relative abundances in our volcano-treated incubations, and also a unique species of diatom. Okay, something that I want to point out here, because I think that is really interesting, is that we found several taxonomic uniques of a same species. And this hints us to think that we got different ecotypes of a same species. So a species that has evolved and adapt and acclimatate to the conditions that are in the Tagoro volcano. So up until this point, we know that Tagoro's nutrients enter to the microbial food chain by the picophytoplankton and the small nanophytoplankton size fraction, and at some point it might be transferred to higher trophic levels by grazing or detritus. So I will really fast with this. Heterotrophic bacteria had small differences in terms of cell abundances, but we found out really interesting things in the molecular analysis because we got, again, differences between our control bottles and the volcano-treated bottles. So something was happening in these prokaryote communities. And something to point out, we got, for example, Rhodobacteriacea, which are nitrogen-fixing bacteria. We got Actinoma marinacea, which are sulfur oxidation bacteria, and an ammonium oxidation archaea, like Chechu found out in La Palma. So it's really interesting to see that bacteria was really diverse and that can have really important implications for the biogeochemical cycles that are occurring in Tagoro. And the same, we've done this analysis to try to get which species were the most benefiting in our volcano-treated incubations, and we got 2 different genus of sarclade that are ubiquitous in the surface oceans, and also Pseudomonas, which are bacteria opportunistic when we got high concentrations of nutrients, so that's really good. And now to conclude, Tagoro's inputs produce a fertilization effect, favor morphologically, ecologically, and probably phylogenetically diverse organisms. Tagoro may sustain primary production on the area and also influence the local biogeochemical cycles. And just to finish, I would like to thank all the team of scientists and technicians involved in these experiments because they were crazy. And thank you so much for your attention.
Okay, thank you everyone. Thank you for having me here. Well, as Eugenio told, I'm Eduardo. I'm from the IGN. And I mainly focus on the seismic swarm analysis and the automatic processing of all of this. At the AGN, we are the Instituto Geográfico Nacional. We are the institution in charge of the volcano monitoring and the seismic activity in the Canary Islands. I will skip this slide because I was going to talk about La Palma, but everyone knows at this moment. And now I'm going to present the results of the last research that we made for the pre-eruptive seismic series of La Palma eruption in 2021. In 2021, we have 11 stations on La Palma from the 11th of September to the 19th of September. This pre-eruptive seismic series started on 11th of September and it ended on 19th of September. And the seismicity migrated from the center of the island at 10 kilometers depth to the surface in less than 7 days. To give you a basis on the normal activity in the Canary Islands, we have like 2,000 earthquakes per year. In this week, we manually located 1,500 earthquakes during this week only, okay? So that's a lot of work to do during this week. So, to give you an overview, to locate, my main issue or my main concern is locating earthquakes, and earthquake is a wave which is traveling through the crust to our sensors. We want to know where and when happened. The hypocenter, and to locate the earthquake, we need to know a velocity model like this. This is a 3D velocity model of La Palma. And we also need to know the arrival time to our sensors. Okay, we need to pick the P and the S wave. You see here, you can clearly determine where the P and the S wave arrives to our stations, and you will say, okay, what's the main issue with that? This is a seismic trace from one of our stations in La Palma 2 weeks before the pre-eruptive seismic crisis, and this is the seismic trace during this week. Okay, this is a problem that we can handle manually. Then, the main issues that we have, the massive workload that we have to the manual analysis is this is massive. We can also introduce manually biases, and we haven't at this moment a velocity model of La Palma. So, well, the automatic analysis that we have at the moment are the typical ones, and we have a 24-hour, 7-day shift which perform the manual analysis for this seismicity. And at this moment, we start to think of how we can approach in a different way this main issue, and then we introduce this pipeline. I'm not going to go further with this, but this model with the FaceNet is a deep learning model that performs the phase peaking, the PNS wave detection. The results that we had is like more than 7,000 earthquakes located in La Palma this week, fully automatically. The seismicity have a different distribution that I'm going to talk later. And this is an example of how this model performs the phase peaking. If you can see clearly, identifies the P and the S arrivals in the whole stations. This is another station, also the same thing. So it performs really, really well. And this is the difference between the IGN manually catalog locations and the new automatic locations. If you see, you can clearly see a clear shift to the west and to the north. Okay, from this range to this range. This is a movie. Okay, this is a fancy movie that shows how the seismicity migrates first to the west, then it stagnates in the west, and a secondary intrusion started to go to the north, and then the eruption happens. Then we propose a new model, or a conceptual model of how this happened. This is from 12th to 16th of September, the seismicity migrated to the west at 8 kilometers depth. From 16th to 18th of September, where almost no seismicity happened, started an inflation, which is coherent with the resolutions from De Luca et al., which made this model of the intrusion with the insert. And from this 18th of September to the eruption onset, migrated from 6 kilometers depth to the surface. If you see the second stage, the second intrusion was only 36 hours prior the eruption. Okay, the magma migrated from 6 kilometers to the surface in less than 36 hours. Okay, during the second, this is the latitude, longitude, and depth plots, which corresponds with locally corresponds with the insert deformation measured by, published by De Luca et al. Also during this third stage, which clearly shows this diatypical pattern, which corresponds with our solutions. And okay, this will be a movie. This will be arrows, which measures the modulus and the direction of the GNSS network that we have at the island, and you will see also the migration to the surface, and you can clearly see how this seismicity is coherent with the movement of the GNSS stations. The length of the stations are in centimeters. You can clearly see this nearest station, how this track is. This migration to the surface. This void over here corresponds with a geological structure with low resistivity that have been previously reported by magnetotellurics and tomographic studies. And okay, sorry, doesn't work. Okay, and well, that's all. That's with the conclusions. We have automatically analyzed the whole week, which gave us more than 7,000 earthquakes. Fully automatically. We haven't performed any analysis by hand. These new features like 3D model can give you a better understanding of these processes. Non-human biases introduced in the phase peaking when exactly arrives. Not high performance computing. I made this computing in a laptop like this. And with this information in real time can give us a better comprehension at the moment what's happening to give information to the civil protection of the people in charge of that to interpret and can give a fastest response. And these kind of tools can be easily applied in any observatory because we don't have these high computer capabilities, and we can do it. So if you have just a laptop, you can perform this kind of analysis. So that's all. Thank you for having me here in terms of.
Hello. First of all, I want to say thank you to all the assistants, both in person and virtually. You have seen me running around all day trying to make things work, but now I finally can talk about science. So I'm going to focus on the impacts of the formation of lava deltas on the marine environment, okay, during the Cumbre Vieja eruption. So again, as we have been talking about this volcano for quite a bit now, I won't go into too much detail for the introduction. As you know, sorry, this volcano erupted on October 19th, 2021, and more or less 10 days later, on October 28th, after making its way downslope, it reached the ocean for the first time, creating this lava cascade that is very impressive. But it wasn't a one-time event. It continued feeding lava to the ocean for a long time. It created several lava deltas. 3 of them merged into one big lava delta. That is the one that I'm going to focus on. And another lava delta was farther north, like in this area, but you cannot see it in this picture. Okay. So, and we were there. Even before the lava reached the ocean, we were called to be present in the area, and we were provided a very accurate estimation of where the lava was most likely to reach the ocean, so that allowed us to sample the area beforehand. And so here we are patiently waiting for the lava to arrive, and here you can see that the deck of the vessel was completely full of ashes. I mean, the crew cleaned it all the time, and it was still always full. Okay, so during this time, we were there during the arrival of lava, and we were sampling, and the main equipment that we used was, of course, the oceanographic rosette, or CTD, that was equipped with sensors of temperature, depth, salinity, but also pH, oxygen, fluorescence, and many more. And it's also equipped with Niskin bottles that we use to collect water samples that are analyzed for many chemical and biological parameters later. And we also use an ROV, a remotely operated vehicle, Liropus 2000, from the Spanish Institute of Oceanography. And we use this, in this case, I'm only going to show a few images of the ROV, but it was also quite useful during these cruises. So we're just going to jump into the results. Okay, first, for context, I'm going to show some ROV images. I won't go into too much detail because this is not the focus of this work. But as you can see, and we had a very nice introduction to this topic from Ramón earlier, you can see different geological structures. So in surface, or in the first few 10 meters of depth, we saw mostly AA-type flows, and then a little bit deeper, we saw some pretty impressive pillow lavas and mega pillow lavas. And a little bit deeper, at around up to 2,050 meters, we still saw lots of breccias and rolled fragments. But the smallest fragments, the hyaloclastite and the ashes, were found up to almost 400 meters depth. As you can see here, the floor is still completely covered in ashes and hydroclastics. And here I also show some pictures of the affection on the venting communities, just to give you an idea of how devastating it was for the local environment. Okay. But now let's focus on the oceanographic variables. So this data that I show here is from the first few days after the first arrival of lava to the ocean, okay? So these are vertical profiles with depth of several parameters, okay? So we have turbidity, oxygen, chlorophyll, temperature, salinity, and pH. And you can always see a reference profile, which is this line in black, that shows you the normal conditions of the area. So the reference stations that are not affected by the volcano, okay? So, okay, I will just highlight a few things from here because there's a lot of information. First of all, you can see that there were anomalies in all the variables in the whole water column. So previous studies only talked about the first few meters for logistical limitations, but we were able to sample the whole water column, and there were anomalies at all depths. You can see especially well in turbidity, because of course there was a lot of turbidity in the water. You can see that they had the shape of like different fingers or plumes that enter the ocean at different depths and with very variable behavior. And another thing that I want to highlight is the pH, which here you can see the complete profiles, but this is in NBS scale. So this is from the sensor, from the pH sensor, and you can already see that there were lots of negative anomalies, but we also sampled pH in total scale from the water sample, so that is more accurate. And here what we can see is a comparison of these first few days after the first lava arrival and 1 month later. So you can see that there was a decrease of roughly 0.11 units of pH, which is a lot. Believe me, that is a lot. Okay. So another one of the most interesting effects that the arrival of the lava had was an effect of upwelling. What does this mean? This means that when the lava arrives to the ocean, of course the water is heated and it becomes less dense, so it has to rise. And when it rises, it has to be substituted by deeper water that is colder and more rich in nutrients. Okay, so, this is data from 1 month after the first contact, but the lava was still arriving, okay? The delta was already formed, but there was still lava inputs. And what we did here were some Tobio transects. Ted 2 this morning explained a little bit what the Tobio was, but I will remind you. We deploy the CTD, and the vessel moves, and the CTD goes down and up, down and up. So we obtain this zigzag shape, and we can get like a very synoptic picture of one transect. And these are the transects that we did. Like in a radial manner, respect to the delta. So the upwelling effect, you can see it here. This is an example from one of these Tobios. I think it's this one. You can see here, this is density, temperature, and salinity. And in all the parameters, you can see how the isolines are elevated. This means that the water is going up, so you can see sort of this movement. And this effect was observed in all these Tobios that I highlight here, but not in these ones. So, and this coincides perfectly with, if you can see the map that is underneath that, that is a map of bathymetric differences between before and after the eruption or the lava arrival. So this means that here, As you can see that there are colors that are more orange and red. That's where there were most, where the lava delta was spreading underwater. And exactly on top of that is where we saw the upwelling effect, which makes sense because that's where the water is being heated. And finally, this is, for me, even more interesting. Another effect that we saw is that the chlorophyll decreased. Okay, the chlorophyll is a pigment that is present in phytoplankton, which is the photosynthetic microorganisms of the ocean. So this is a proxy for how much phytoplankton there is in the water, okay? So what you can see here is a comparison, okay? It's like a timeline, and we see before the lava arrived, the first few days after it arrived, and 1 month later, okay? And the different colors are the distance respect to the lava delta. So, for example, the gray line is reference stations that are very far away. That's the normal conditions. And the green line is 1.5 kilometers from the delta, and the yellow is 1 kilometer from the delta. And then in the last cruise, instead of doing just stations, we did the tow yaws, so we have more boxes, we have more colors, because we can split them in slower sections. Okay, so what does this mean? This means that if we compare, for example, the yellow boxes, which are always 1 kilometer away from the delta, we see that in just 2 days after the lava arrived to the ocean, the chlorophyll decreased at 41%. But if we compare to 1 month later, there was a 65% decrease at 1 kilometer distance. And if we go to the red box, which is even closer to the lava delta, this increases to up to a 69% decrease. This means that almost 70% of the chlorophyll that was present in the water before the eruption disappeared, even 1 month after the eruption. And also you can see, because in the tow yaws we only reached 2.5 kilometers from the delta, and you can see that at that distance we still had very, very, very low levels. So this means that we did not delimit the area of affection. So it's at least 2.5 kilometers that this effect was present. Okay, and just a very brief discussion about this. I want to talk about another example, which is in the Kilauea volcano in Hawaii. And here they saw in 2 studies, this is from 1995 and this is from 2019, they also saw the upwelling effect that I explained. The water was heated and it rose, and it was substituted by deeper waters, and these deeper waters brought nutrients to the surface, okay? And what this created was a phytoplankton bloom. The phytoplankton was, it promoted the growth of phytoplankton, and there was a huge bloom, okay? And they saw, well, yeah, a huge phytoplankton bloom. But in our case, this would be the case of La Palma. We also have this upwelling, but we don't have a phytoplankton bloom. The phytoplankton was not positively affected. In fact, it was very negatively affected, obviously, because we saw a 69% decrease in chlorophyll. So what did it cause a bloom in Hawaii but not here? That is the open question that will have to be studied in the future. The simplest explanation, and what I think happened, is that eruptions in the Canary Islands cause more turbidity in the water because there's more ashes and hydroclastics. It's a different kind of volcanism compared to Hawaii. So, of course, if there's this much turbidity, it doesn't matter if you feed the phytoplankton. If it doesn't have light, it's not going to grow. So that's the simplest explanation. We're also working on other hypotheses, but it's a very interesting comparison. And yes, just to conclude, the effects of the lava delta formation on the marine environment were, first of all, anomalies in all the physical and chemical parameters in the whole water column. particularly a very high turbidity and also decreasing pH, in oxygen, temperature increase, etc. There was also a boiling effect caused by the arrival of lava, and there was a severe depletion of chlorophyll up to 69%, which suggests a negative effect on the phytoplankton communities. That's all. Thank you so much.
That's true. Okay, so thank you very much for the invitation. In name of my institute, I'm very happy to be here. And I'm here to give a presentation, to give a talk that is entitled "Use of Remote Sensing for Volcanic Eruption Monitoring the 2021 Eruption on La Palma Island, Spain." So I would like to present the result that we obtained from the use of drones and satellite remote sensing during the volcanic eruption that, as you know, took place in 2021 on La Palma Island, specifically in terms of risk assessment and also showing the impacts of the lava flow on both the terrestrial and the marine environment. So, as you know, this volcanic eruption started the 19th of September in 2021, and it lasts 85 days of eruption until the 25th of December. It emitted large amounts of magma from a single, from multiple vents aligned in a single segment on Earth's crust, and the lava destroyed everything on its path, affecting approximately 3,000 buildings and provoking the evacuation of approximately or more than 8,000 people. And 10 days later, the start of the volcanic eruption, the lava reached the ocean and generated a lava delta that was locally known as Fajana. And this lava delta was formed when this lava flow was solidified when entering into contact with the seawater. And as a result of this interaction, a smoke column that reached heights and tens of meters was generated, and that provoked that the authorities established a security perimeter of 500 meters that vessels could not access. So here, I want to talk about the use of different techniques involving remote sensing imagery, because volcanic eruptions are hazardous and poses a major challenge for direct observation on the ground. So in that sense, the use of these remote sensing technologies can help to avoid risks during the observation of these phenomena. So a story talking about satellite imagery, the main advantage is that you can achieve a higher coverage, although it relies on meteorological conditions, with the exception of thermal and radar sensors that can work under cloud coverage and during the night. But if we talk about drone imagery, they provide thinner spatial resolution than satellite imagery that sometimes is too coarse to monitor these kind of events in near real time. And also, drones provide data on demand with a higher control of temporal resolution. However, we have also some disadvantages of the use of the drones, since the coverage is smaller than using satellites. Also, their deployment on the field is limited by battery autonomy, and there are a lot of bureaucratic procedures involving the request of some permission for flying. So the first study I want to discuss or present you is this one, in which we use 3 different drones equipped with different sensors for the monitoring of the volcanic event in near real time during the volcanic eruption. We were there between the 1st and the 3rd of October, that were some days after the formation of the first lava delta. And we used the drone data and also our sampling device to monitor different volcanic features in the regions proximal to the vents and in the regions proximal to the lava flows. Also, we monitor the appearance of thermal anomalies in the lava delta, and we collected water samples close to the lava delta to analyze the impact of the lava into the marine environment. So using the information provided by the topographic products that we generated with the photogrammetric process, using the RGB information that we get from our drones, we could elaborate a slope map using the digital elevation model that could highlight the main topographic features of the vent regions and the proximal lava flow. So with this information, we were able to use a simple probabilistic model to predict the most likely pathway that could follow the lava flow. And we also, it is marked in red here in the figure, and we also represented the real path that follow the lava flow in this vent region, and we could see how powerful are these tools to provide information in near real time to help authorities and decision makers to predict the impacts of this or the direction that could take this lava flow, and also to evacuate people that were in the most probably path of this lava flow. We also were monitoring a region of 35 hectares in the lava delta, and we could determine that in this period of time between the 1st and the 3rd of October of 2021, it was generated a formation of a lava delta of 28 hectares. So we monitored it with a thermal sensor mounted on our drone, and we were able to detect some thermal anomalies and different ground features with temperatures higher than 150 Celsius that saturates the sensor and that were corresponding to this volcanic activity. And we also use a multispectral sensor of 10 bands monitoring this area of banana plantations that are one of the main economical resources of the island. So we were able to generate a false color composite that is this panel B of the figure, an NDVI index that highlights the vegetation in this panel C, and also a supervised classification based on the spectral information provided by the multispectral sensor. So with this information, we could estimate a region of 28 hectares affected by the lava cascade in this region. Finally, we took some water sample close to the lava delta to analyze the impact of the chemical and physical reactions that could happen in the marine environment in these areas close to the lava delta. So we took 6 samples close to the lava delta and some samples in areas that were not affected by the lava cascade, and we measured salinity, temperature, pH, alkalinity, dissolved compounds. And observing these salinity and temperature profiles, we could see how they both increase in these regions that were close to the lava delta. In addition, the entry of some gases coming from this volcanic material triggers some chemical reactions that were also affecting the pH in the water. And now I want to send this second study in which we use or we try to test a new framework, including atmospheric and also glint corrections for satellite imagery involving Sentinel-2 and Landsat-8 multispectral devices. And we also try to monitor the temporal gradient and evolution of some water quality parameters of relevance, such as turbidity and chlorophyll A. So looking at this temporal sequence on the left, we have the turbidity maps, and on the right, we have the chlorophyll A map previously to the volcanic eruption, during the formation of the lava delta, and after the formation of the lava delta. So if we look at the turbidity maps between the 10th of September and the 26th of September in 2021, we can see how the turbidity values are between 0 and 2 FNU. And after the formation of the lava delta, we can see how the appearance of a new turbidity plume with turbidity values between 10 and 20 FNU in the west part of the island that was extended into the west-south part of the island. Then from the 19th of November, we can see how these turbidity values were coming back to the original values pre the formation of the lava delta. So this turbidity plume that involves the entry of nutrients and some some trace metals to the seawater could also involve the appearance of some plankton peaks or blooms during this period. But surprisingly, and coinciding with the data that was presented in the presentation before this, we can see how no chlorophyll A peaks were observed during this the formation of the lava delta and during the eruption period. So observing the satellite images after the eruption, we can see how the water quality parameters return to their original values before the volcanic eruption, even with the formation of these two lava delta that finally were of 5 hectares in the north part and 44 hectares in the southern part. And we can say that the marine environment could recover their state in a relatively short time. So, conclude, I can say that the advantages of using the drones to monitor and manage the evolution of these volcanic events outweigh the disadvantages. So, this methodology is applicable in real time, so it provides information that is very valuable for authorities and decision makers, facilitating the evacuation of populated areas and assessing the situation. And using the satellite images, we could observe how in this area that was close to the lava delta, the turbidity was significantly affected, although there was no pronounced chlorophyll A change observed during and after the volcanic event. So thank you very much for your attention.
And discussion.
Oh my goodness, what an incredible session to finish off with. It was so packed. Your students are amazing, really interesting stuff to dig into. I'll just start with a question from the floor. If anybody has a question, I know we've got 1 or 2 online as well. Is there anybody here who would like to ask a question from one of the people who spoke this afternoon? Yep. You might have to come a bit closer, Ryan. Thanks.
Yeah, mine's for Juan Pablo. So when you saw any, or did you see any clustering, like really short clustering of hydrothermal vents? When you saw that, did you consider a criteria to whether have them as one whole hydrothermal vent or consider them all separately if they're all in a really short spatial distribution?
Yeah, thanks for your question. No, when I say clustering, yeah, the groups are for the stations, not for the individual vents. So it was just for how close they were, but it was kind of a visual approximation, not a numerical. I mean, we didn't consider any specific measurement just to say that is a cluster. It's just a visual, just to say, okay, we have a bunch of stations here and they have kind of the same characteristics, but we have another cluster here and they have different, but it's just as a matter of distance, but a visual distance.
Thank you. I think you had another question, did you?
Then any, did you try and look at any temporal changes and any changes in the fluid velocity over short term or long term?
Yeah, thanks. So, yeah, as you said, this survey was in a very long temporal term. So we also took a look to see if it was a temporal variation between these very close stations, and no, there was no variation. That's why we consider this temperature in this heat calculation, because if not, we cannot use all the different measures to estimate the heat, because if not, we have to estimate the heat flux per year instead of like the global heat flux for the study.
Juan Pablo, thank you very much indeed. Anybody else? Yes, we're coming back to the Durham cluster.
Thank you. My question's for Alba. Over the 2.5 kilometers that you saw the change in chlorophyll, did that marry up with any pH changes? So you saw a decrease in pH, I think. So did that reflect any carbonate compensation that may have affected the phytoplankton?
Okay, let's see if this works. Okay. Okay, so I guess you're asking if maybe one cause of the phytoplankton decrease could be related to the pH. There were anomalies in pH, like I showed. I mean, it's worth exploring this possibility, but I don't think it's the main cause, because the anomalies in the physical chemical anomalies were very strong, but very more or less close to the lava delta. Okay, they weren't reaching huge distances, but the phytoplankton decrease, I mean, it's not that it reached 2.5 kilometers, it's that we only got to 2.5 kilometers, and at that distance it was still incredibly low. So it's probably several more kilometers of affection. And the pH, the pH affection is not that far away. So I don't think it's the main reason, but it's a variable that we should take into consideration. Yes, thank you.
Thank you very much, Alba. Yes, Pablo.
Bueno, Juan Tomás, my question is for you. You mentioned something, dropping there the ball, that we have less than 1 million year old volcanoes west of the Canary Islands, but you didn't have an explanation for it. So what is your opinion? Is it petit volcanism? It is part of the Canary Islands hotspot anomaly, or what is your interpretation of that very recent volcanism?
I think these volcanisms are related with the context of the Canary Island, but they are not far from the hotspot. I think the Canary swell produced the deformation to the west, a flexural deformation, and this deformation produced a differential topography in the base of the lithosphere, and this could produce an adiabatic intrusion of magma. So it's related with the context of Canary, but not related with the hotspot, my opinion.
Thank you very much. Anybody from the front row perhaps have a question? Yep, Juan.
Okay, thank you. My question is addressed to Eduardo. Of course, as you mentioned, when we classify and pick the S and P wave in a seismic signal, we create bias, right? But I would like to know if it's possible that these automatic classification methodologies create their own bias.
Yes, that's a good question, because many studies have regarded on this topic, and it will depend on how you train your deep learning network. But I didn't train it. I took the main model that the FaceNet developers use, and that they train it with the PNS waves from Northern California, and I applied directly to the La Palma. And when they analyze the bias respectively to the Manon analysis, and even if you filter the signal, you will see the PNS wave arrival at different times, and the residuals between the Manon analysis and the automatic analysis, at least with FaceNet, are really slow. Sorry, it's really small. But it will depend on the seismic network that you, not the seismic network, but the seismic record that you have, and the filters that you apply. If you see the signal without filters, many times you will pick the PNS wave phases earlier than with filter. So even the developers of FaceNet told you that when you apply the FaceNet or any kind of deep learning method, you have to filter and see the waves unfiltered to see if there's any bias. I didn't tell because I hadn't time, but I made all this kind of tests to see the biases and I refer to the previous studies than mine. Yeah. Okay.
Yeah. Just one more question. Juan, here we are.
It's a small question to Alba. When you were talking about the upwelling process, you show some graphics with different variables, the profiles. And one of them says potential temperature. What do you refer to that? I don't know. It's just curious.
Okay, this is just an oceanographic variable, very similar to just saying temperature. It's just that potential temperature eliminates the effect of pressure on temperature. So it's the pressure. It's the temperature that the water would have if you took it to surface without it losing heat. So it's just an oceanographic term to eliminate the effect of pressure on temperature. But we are talking about 300 meters depth. So it's at this depth, the difference between temperature and potential temperature is almost nothing. So you can consider it as if it was just temperature. You're welcome.
Thank you, Alba. We actually have a question for one of our online delegates now. Roger Southern of University of Derby is with us. Katie says hello, Roger. A question to Juan Pablo. How do cones form on the deep ocean floor when we would expect any explosive activity to be suppressed by hydrostatic pressure?
I don't understand the question. it's kind of very technical for me. What does she mean?
How does the cone actually form underwater? When
the cone?
Yeah, the cone of the volcano. How does it form if it's got this hydrostatic pressure in pushing down on it? How does that allow the cone to form?
Yeah, but that's kind of a geological question.
It's coming from a geologist. Yes.
Thanks.
Thank you. Thank you.
Well, I try to make the answer well. Previously, I speak about the deep erosion, submarine erosion. In this case, the problem is how so big hydrostatic pressure is possible to the gassing of the lava. But for example, Tomás showed us tephra from very deep ocean, I think 5,000 meters, and you can see the tephra have a lot of the vesicle, the middle. This means that it's possible the gassing at a very high hydrostatic pressure. You can see also the actual volcano, Mata, and Northwest Mata, and I saw in my presentation the 2 videos about this deepest eruption. You can see the production of pyroclast. In this case, for the produce pyroclastic material is no problem, and for the growth, the edifice, the pressure is not so big that can be not possible to grow the volcano. No problem with that.
Ramon, thank you very much indeed. Yes, we're coming up here. We've got a few hands up. This is very promising. Lawrence, over to you first.
My question's for Claudia. How long do you expect this fertilization effects in the microbial community to last after an eruption before it goes back to what it would be normally?
It works? Vale. We studied the current hydrothermal vent effects, so it's not related to the eruptive phase, sorry. So now what we are seeing is that there is a continued passive shallow hydrothermal fluid inputs into the water column. So the communities will be adapting and acclimating to these conditions and then living. So if we have the right conditions of light and the necessary nutrients to grow, I think that they can live there happily ever after, no? As we say in the movies. So yeah, maybe we will not see like phytoplankton blooms like living for 50 days, because this is not the case, but that there is a primary production that is higher than other areas of the El Hierro Island, probably, yes.
That's great, thank you, Claudia. We have a question from Jaime Coello of Fundación Coello Bravo.
Thank you. I have several questions for Montserrat Román. I would like to know if you are working or anyone are working in a dangerous volcanic map, because I think it could be a very good tool for you to make decisions. That's my first question. Second, are you reviewing the decisions or how the PEVOLCA work in an independent basis? Are doing any review by any standards in order to learn about what happened and in order to have some conclusions about that? And we have been talking a lot about El Hierro and La Palma, but we have Tenerife in front of us also. And you know, it's likely we will have a volcanic eruption in Tenerife in the next future. Are we going to do any? Are you planning to do any simulacrum before the COVID? I know that you were working in organizing simulacrums and exercises with the civil society, and I don't know, just work on that side. I think Tenerife would be a very difficult scenario if that's the case of a volcanic eruption with more than 1 million people living here and 5 million tourists. I don't know if you are working in anything about this. Thank you very much.
Okay, I will try to answer. So I think Eugenio can help me or someone else. So the first question, yes, we are now very near to have new maps for risk update in all Canary Islands, not only Tenerife or La Palma. And this is a work that the Felsic is working now. We meet 2 weeks ago with a person that is now developing these maps nowadays, and we thought that in few months we can update our plans. Also the Cabildo's specific plans in each island, and this is very important to begin and be nearest to the territorio, to to the territorio and manage the risk better that we are now doing. I think there are a lot of work to do in this question that be nearest to the maps of danger, maps of risk, and manage in a different way, perhaps this risk in the Canary Islands. The same maps with the same update. I think we will have also new scenarios that are different in Tenerife than in the another islands. So we have learned a lot in La Palma. We can update our PEVOLCA, I think, with guarantees, with all the learnings of La Palma, but we have to add all the scenarios in Tenerife, Teide, that are very, very, very different of the other kinds of eruptions that we can have. So the civil protection decisions and all the decisions about the self-protection of the population and the prevention, all of this will be different with this new analysis. And it's very, very important to first update all these plans with these maps and show these maps to the population and do it normal and work first of all with the groups of action, firemen, sanitaries, police, logistic, technicals, and immediately later on with population when in the administration and all the actors can be trained and in this area. So I don't know when we will update formally the PEVOLCA, but the most important is that we know that the areas that we have to improve are very well located and identified. And I think this is the most important, because sometimes the process of update a plan is like with the administration is very complicated, but it's not the first time. I am not saying that we will wait the next eruption without the PEVOLCA update. No, it's not that, but it's not a good comparison, similar, but for example, we, in the eruption in La Palma, we have a protocol for animals evacuation that it was not approved formally, but in fact we put it on. So I think the most important thing is we have a lot of things very identified. We are waiting for the lessons learned with the committee, scientific committee. This, I think, it will be perhaps the most not difficult but more complex, I think, because we have to be more close to the civil protection with the scientific information. So from the civil protection authorities have to think what we need from the scientifics, not all the debate, perhaps. So perhaps they have to debate without us for free, and later on we have to say, well, today we want to know this, and with this, the authorities will have to do to apply the self-protection for the population. So I don't know if I answered the 3 questions more or less. Thank you.
Montse, that's very comprehensive. Thank you very much indeed. Yes, Ramón, you have your microphone. That's great. Thank you.
I'd like to give a question for you, Tomás. Well, it's related to the early question by Pablo, because you saw, I know the work, the paper you saw in the presentation. I think in your presentation and this paper, there are several things I think very interesting. For example, you saw very strong tectonic affected the oceanic crust to the west of the Canary, and also you present the very expanded magmatic activity in the oceanic crust. No, you mentioned several mounds, several simum. Also, I know for the paper in the southwest simum region there are all the simum, but they have very recent activity, volcanic activity. I think this scenario is, I think, is a view very different for the previous, to consider the oceanic crust more or less very stable, very not affected so much by deformation. Located, the magma is located in several places related to host spot probably. And I think this is a new scenario, and what did you think about this scenario to relate it of the hotspot hypothesis, like it's made in Hawaii, and sport for another interplate volcano?
I think the magmatic features that we observe it in, especially to the west of El Hierro. In the northern sector and southern sector, they look like all features with slides, with several different features. But in the west of the El Hierro, I think it's a very modern volcanism. I think it's a volcanism not related with the hotspot, and I think it's the presence of differences, the topographic differences in the lithosphere can produce several magmatisms. It's probably the first time that so deeper volcanoes are recognized in this context. But also they are in subduction zones where the lower plate is bending. Also appears minor volcanoes related with the flexure of the lithosphere, probably with a similar mechanism. Difference in the base of the lithosphere can produce adiabatic intrusion of magma. I think the lithosphere is, oceanic lithosphere is not so stable that people think is a more rigid lithosphere, but is crossed by fracture zones that could be reactivated and could be produce deformation in the upper layers.
Thank you. Thank you.
Thank you very much. That's great. We're going to go to Pablo from Felsic. I think you had a question for the panel.
Well, I think I will have many for each of you, but taking the opportunity of Montse having here and us having many debates, I would like to ask about, well, first of all, I think we will have this meeting to reflect about how we can serve better the society, but second, I think in general, civil protection has to also be self-critic on not having your own opinion. And sometimes, you know, you feel that, or my modest opinion is that you cannot distinguish who is right and who is less right about the scientific information that you are being presented. And I think this is something that can be fixed if you realize you need to have on board your own specialists that filter a little bit the information that comes from the scientists. Second, is that most European countries usually commission maps not to a single group or a single group, but they tender with their own criteria what they want from the scientific community or from the geological surveys. Say, we want this, and we want it with this specification. Don't give me whatever you have in your shelves and pack it to use in this case. Because, you obviously it's better than nothing, but it's not a leap forward, it's not something that, and it will be very difficult to identify who is or what are those criteria if you don't have your own opinion. So I would be more happy to see volcano specialists in the Canary Island government on the side to analyze and to be able to give the criteria that you need because you're working for yourself rather than outsourcing the work to the scientific community with their own specialty. So I think tender the work, tender with criteria, and see who provides what, and then manage the information to create community models rather than one specialist. Sorry, it's not something for you to answer, and I think I will not put you in the spot, but I would like to make this open. My question, probably for proper answer, is for Ramón. So I would say there is a hot debate and a controversy in the Canary Islands of how to call the lava deltas. So can you give us your opinion about the difference between fajanas and Isla Baja?
Yes, I try to explain. I think the mistake arrived from the San Juan eruption, because in the north part of the La Palma there are through fajana. There are these fajana are produced by the stone for the upper part of the cliff go down and produce for accumulating and produce a more or less plain material, plain terrain. In this case, when the San Juan eruption arrived, the people think the form of the terrain of the lava delta for San Juan is very similar to the North Fajana. In this case, they name it, and this part of the island Fajana of San Juan. And after, I think the mistake occurred again at the La Palma last eruption. The difference is in one case is the lava go down and form the lava delta, and the other thing the stone go down for several thousand years, etc., and produce this more morphological terrain similar. But in Canary, the through lava delta is named Isla Baja. For example, in Los Silos here in Tenerife, and El Hierro also there are several. No? And this is a discuss along the eruption, and the two universities, Las Palmas University and La Laguna University, make a paper and distribute it with the media, etc., to discuss that. And this paper collaborate not only the geologists and also for philologists. People, one old teacher from Las Palmas University, he is considered one of the most important person who know the Canarian toponymy. And this person also explained the difference between Fajana and Isla Baja. But you see, the media is the media, and more or less developing this term, and now it's very difficult to change this meaning. But it's a mistake. I think this is a problem.
Ramón, thank you very much for that very clear description. Any more questions from here? We've only got about 10 minutes, so we've probably got time for 1 or 2 more questions.
I have to answer this.
Thank you. Thank you, Montse. Thank you.
So it's complicated to answer in Spanish, or because it's very interesting, these questions. In the civil protection, we have the natural, technological, and anthropogenic risks. So this is a multi-risk. In civil protection, it's important to have in our staff specific characteristics of the technicos that are working with us. But for example, it's necessary to have now we have a geographic one or geologics. Also forest engineers, but in fact we should have a lot of different specialists, and also for sure be able to manage emergencies, big accidents, and situations that are a lot of population involved, and very difficult situations that we have lived recently. So it's not easy, but I think it can be a model to reach and add specific people that are with specific knows about. I don't know if there is a degree of volcanology. I don't know if exactly. So also can be a lot of different areas. So it could be also difficult, but it's true that, for example, in Italia, is another model, another system. They have, as you comment, there are people inside the civil protection structure with this very specific with this area, like scientifics or volcanologists, I think, I remember. So we have to think about this, and we have to think about what we want in the next eruption, what changes we have to do in the scientific committee with the reasons that I explained before, and think about, I don't know, how if we can, for example, make the committee more flexible. Perhaps there are some organisms, administrations that are in this committee, but perhaps we can add more people, or I don't know. It depends of the emergency. Always listening, pues IGN, in this case, with the responsibilities in this area. In Spain and in Canary, of course, and listen, and perhaps so we can add more people at this moment, for example, and also in the civil protection structure, I think. So first of all, we have to be more people, because we are 4 or 5 people for our emergencies. We realize, everybody has realized that in Canary Islands, the emergencies when happens are the manual emergencies, not day by day or raining. No. When the emergencies arrive to the Canary Islands are emergencies of the manual, of the civil protection, what you study, when very low occurrity, very low possibilities of occurrity, but when it happens, the impact is very, 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 very high. A lot of people involved. The characteristics of the Canary Islands, ultra-peripheric region, islands. You have to move a lot of people. The logistics is very, very complicated. I don't know, a lot of things, no? So we have to think about a new model. This question is very accord to the situation, and we have to think we have to think what we want in the next eruption. And the second question, yes, also we have to change this. So we have to be who define what we want in these maps, and I think we have begun, because with the conversations now with the CSIC, the CSIC is saying, please tell us what you want, not what you need. So I think we have to improve and think also about this, about what we want from these maps. And I think we have to mature now, no sé cómo se dice, be mature with this area. There are a lot of work in nowadays and in these months, that we have to work very hard in this update of the PEVOLCA, but with the maps, and also it's what we say before, this emergency that occurs once every, I don't know, and it's a handicap for us and for the population, and we have to think about this very, very hard. Thank you.
Montse, thank you very much for that very complete answer. It's a very difficult question, but it's great to hear that those conversations are being had and that those thought processes are in your mind, because it's critical. Any more questions from here? Yes.
Sorry, Montse, but it's great to have you here, and it's very good to have you here, because we can ask you questions that are, there are a lot of people wondering, for example, in La Palma, they are beginning to give permission for the people to build in the lava flows. Are they listening to your work, or is there any coordination between the planners, the people who are going to decide, or the local authorities that are going to give permissions for building in the lava flows, with you that are working in a map that is going to be a map of volcanic risk? Because maybe your map is going to say you shouldn't build here, because in the future, a new volcanic eruption could happen there, and then who is going to respond for that, answer for that? I think there are a lot of questions in that topic, and I think they are running really fast in La Palma. It's my opinion. It's only my opinion, I have to say, but I think they are running very fast, and they are not maybe considering this side, and I think it would be very unfair to condemn the next generations of people from La Palma to suffer the same if they don't take care of this information you are going to provide. So I don't know, what do you think about it, and I don't know if there is any connection or coordination between administrations in that topic. Thank you.
So what we are now realizing is that civil protection has not been when the territorial development plans. So now we have to improve this, I said before. And we live in volcanic islands, so we can move. I don't want to move from here, and we have to be nearest to the population. We have to begin with the people in school. We have begun step by step with another risks, but also we have to do it with the volcanic risk. I know scientific are doing a lot of information with the schools, I know this, but we have to explain about evacuations. We have to explain about your house can be damaged, or you can lose your house, no? So now the work now is the first, because it seems very simple, but now when we will publish the maps, I think will be one day and the other day. I think will be now our first step, I think, to begin to normalize. I think it's I think it's really normalized. But when it happens, you don't want that it is there, and you don't want to lose your house. No, I think it's very managed. I think it can be very good managed. I think can be I don't know how to explain, to create a culture above the possibility of eruption. So will happen. So I can lose my house. So how can we arrange this, or how can we manage this, or what have to do after this the public administrations, or what have to do you as a citizen, or how can you protect yourself with so many different ways. So I think this is not much more. So we have to be nearest with the risk and the population. It's like, it seems simple, but we have to do this first step and show the map, show all the evacuation areas, so continue with the training. That it's true that it was previous exercise pre-COVID, so it's a very tool to improve and to train, and not much more. I think this is the way.
Montse, thank you very much. It is indeed the way, and people will be very grateful for that effort. It's not easy to publish these maps. It's not easy to deal walking forwards, but it's absolutely vital. We live in these beautiful islands and we want to keep living in them. I just want to say thank you very much to all the panel and pass you over for wrapping up from Eugenio. Thank you.
Well, thank you very much to everybody to be here. I think that we have already finished this meeting. I hope that you enjoy this full meeting and you learn a little bit more about the submarine volcanology in the Canary Islands. And the more important thing is that you can also extrapolate the science that we were doing here in the Canary Islands to every single place in the world. So that's all. I think that thank you so much for all the persons that have already presented every single presentation here during this day. I know that you are really busy guys, and that you've got a lot of things to do. So for this reason, I appreciate that. I really appreciate that, to take the time to prepare the presentation, to come here a whole day and present it. Not only the person that are here today, but also online. So thank you so much for the people that are online, that they were presenting also online. Thank you so much, Sharon, also. Always to be here and to support this second symposium of submarine volcanology, because it's really important for us, not only because we are friends and we know each other for a long time, but also because you are doing a really great job in the communication of the normalization of this situation, of the volcano and the submarine volcano around the volcanoes of the Canary Islands in general, and also to bring all these new guys from all around the world that are also bringing new energy to the Canary, new energy to the science, and we are completely sure that we are going to do a lot of things together. Also, I don't know if someone else that I have to say thank you. Oh, for sure, the organizer. Always say, Alba, Juan Pablo, yes, thank you so much for organizing everything. No, I know also, Juan Pablo, that your little baby is a little bit ill, but you are still here. So thank you so much, because it's really nice for that. And that's all. Thank you so much.